So let's get started. So in the last class, we just went over some of the basics in probability. I defined the probability space, the event space, and the probability measure. And we saw some reasons as to why these definitions are important, particularly in the case when the sample space is uncountably infinite. The standard tools, for example, you can't really take the event space to be the set of all possible subsets of the sample space. So in these cases, you have to restrict yourself to a class of subsets of the sample space, and that essentially should form a sigma algebra. Right? And we also saw, right, so here are some examples. So let's suppose that your sample space is this, let's say the outcomes of a roll of one die. In this case, what is the smallest event space? Just one outcome. So remember, the event space is a class of subsets of omega. Yeah? What do you mean by the null space? It's a class of subsets, right? So what is the smallest set of subsets that forms a sigma algebra? Correct. So this would be the set containing just two elements, which is the null set, because the null set has to be an event, nothing happens, and everything happens. It's a trivial event space. It doesn't give us any information about the any non-trivial information about the events of the space. What is the smallest event space containing these two sets? So you need the empty set, you need omega, and of course you need these two sets, 1, 2, and 2. What else do we need?
3, 4, 5.
Okay, we need the complements of both. So we need 1, we need 3, 4, 5, 6. We need 1, 3, 4, 5, 6. What else do we need? Just that? Anything else?
2, 3, 4, 5, 6.
2, 3, 4, 5, 6. Anything else?
So why 2, 3, 4, 5, 6?
2, 3, 4, 5, 6. The union of this one and this one.
Then 1 should be
Correct. So why is that? Why should just one be there?
complement of.
Complement of? Yes, exactly. So they should have one. Anything else? That's omega. That is there. Anything else? Yeah, I guess that's it. So what is the largest event space? The power set of all possible subsets. And how many elements are there? 2 to the power 6. So in the special case where omega is the set of all real numbers, or maybe an interval of real numbers, after all, we need a sigma algebra to work with this, and we will frequently use this sigma algebra, particularly when we talk about random variables. So the sigma algebra that we typically work with is this sigma algebra, which is generated by open intervals or half closed intervals, right? And this particular sigma algebra is called the Borel sigma, right? It's not easy to see that this does not contain the power set. There are in fact like many sets which are not part of the Borel sigma algebra, but this kind of sigma algebra, it contains all, at least most of the events that we are interested in, right? And in fact, there's another sigma algebra that we also work with called the Lebesgue sigma. Right, and that is a sigma algebra which is essentially the Borel sigma algebra, and you also add some sets which have so-called zero measure in. Right, let's not worry too much about what these mean, but you should know these terms. All right, so in the last class I also defined the probability measure. So it's any function from the event space to the interval 0 to 1. So for every event, you assign a number between 0 and 1, and this function should satisfy certain properties. One, it should give a measure of 1 to omega. And if you have a collection of disjoint sets, at most countably many, then the probability of the union, or the measure of the union of these sets, should be equal to the sum of the measures. Right? Yeah, we're out of space. If possible, can you try to check in one of the rooms if there's an extra chair? We'll move to a bigger classroom in the next class. This is there in my course webpage. I'll again, once you join the Google Classroom, you'll find a link to that. So I will post all of these. Okay, fine. So in the last class, we also saw why we assign probability measures to events and not outcomes, because in many cases, particularly when the sigma algebra, when the sample space is uncountably infinite, it is not possible to assign a meaningful probability measure to outcomes. All right. So the next important concept that we need is that of a random variable. And the random variable is essentially a map. It's again, although it's called a random variable, it's actually a function. And it basically maps outcomes to elements of the reals. Right? And it's not just any map, it has to satisfy the property that intervals correspond to valid events. Right? So every half-closed interval, again, there are various definitions of this. You can look at open intervals or closed intervals or half-closed intervals. And every half-closed interval should correspond to a valid event in your probability space. Right? And this is the reason why we look at these random variables is that now you have an original sigma algebra. You're essentially mapping this to the Borel sigma algebra, so that you can develop your entire theory of probability purely based on the Borel sigma. So you're sort of hiding all of that information. So essentially the information about which specific probability space you're working on becomes irrelevant. You can just look at random variables, which basically corresponds to probability spaces over the reals. And one way to look at this is to take this particular example of an infinite sequence of coin tosses. Right? Suppose I have a coin, I toss it infinitely many times. It's a fair, assume that it's a fair coin. Actually, the bias doesn't really matter. But suppose I'm tossing a coin infinitely many times. Can you construct a random variable for this infinite sequence of coin tosses? Let's suppose I have heads, tails. So I need a valid map to basically map a sequence of infinite coin tosses to an element of the reals. Let's say that I want a random, from this, I want to construct a random variable, which is in fact all the outcomes are mapped to numbers between 0 and 1. Any guesses?
It's like binary code real number.
Okay, can you be a little more?
Let's say X is 0 and tail is 1.
Okay, so heads, let's just for now label a head as a 0 and a tail as a 1.
Then it's like a space of 0 and 1, like n dimension.
Correct. So basically this is a sequence of bits, right? Zeros and ones. And I can represent this as, let's say, 0.010001. Right? So this looks like the binary representation of any number between 0 and 1. Correct. So I can look at x. So let us say that bi is 0 if the ith toss is a head and it's 1 if it is a tail. All right. Now I can represent this as a sequence of bits b1, b2, b3, and so on. Now, how do you represent this as a real number?
To the power of -1 into b1 plus.
Yeah.
2 to the
So,
power of
so my x would be what?
b1 by 2
Correct. So b1 by 2
plus b2 by
plus
b2
b2 by 4 plus b3 by 8 and so on.
summation bn by 2 to the
Correct.
power of n.
It's basically summation I going from 1 to infinity bi divided by 2 to the power. Right, so there's a 1-to-1 map. And is it true that every interval corresponds to a valid event? So for example, let's take the interval from 0 to a half. Okay. What event does that correspond to?
Okay.
So if x is between 0 and half, what can you say about the sequence of bits? What should happen? The first b1 should be equal to 0, right? So what event does that correspond to? The first toss is a head. Correspondingly, if it is between a half and 1, then the first bit should be a 1, and that corresponds to a tail, right? What about the interval 0 to a quarter? The first two elements are a head, right? Similarly, quarter to a half corresponds to the first two being head tails, right? And so on. So you see how this is going, right? So every interval here corresponds to some event which corresponds to sort of subsequences, right? So you say that, let's say that you want to know if the first, let's say the second toss is a head, the third toss is a tail. Now that corresponds to some interval, right? And now for every interval, I can assign a probability measure. So what, in this case, what is the probability measure of getting between 0 and a half? So, okay. So what is the probability that, so this is the, so I have this random variable, right? I've defined the random variable x as summation I equal to 1 to infinity bi by 2 to the power I. We have some intuition as to what this looks like. So now what is the probability that x lies between 0 and half. Right? What is the probability that x lies between, let's say, a quarter to a half? 1/4. Right? Now, if I take any interval, what would be the probability of getting of getting that interval? So what would be the probability that x lies in some interval a comma b? B minus a. Are you convinced that it is always b minus a? If you had to prove this, how would you do it? Maybe not a fully rigorous proof, but I want to make sure that I'm convinced that it's indeed b minus a. So what kind of intervals do we know the probabilities of? Exactly. So as long as, so I know that, suppose I take probability x in, let us say, j by 2 to the power I to j plus 1 by 2 to the power I. What would this probability be? You're convinced that this is 1 by 2 to the power I? What event does this correspond to?
Exactly.
Correct. So basically, you look at the first I tosses, the probability of getting one particular sequence would be would correspond to getting an x in this particular interval. Right. So this is some realization of b1, b2 up to bi. Correct. So no matter how large I is, I know the probability of this. Now, if I give you an arbitrary interval a to b, can I approximate it, at least approximate it, using intervals of this particular form? Do you all agree? Yes, no? Anyone says no, it's not clear? It's okay, don't feel shy. All right, so it's clear, right? So given any interval a to b, I can write it as a disjoint union of intervals of this particular form, or at least approximate it for some large enough I. Correct? So then what should the probability of the union of disjoint intervals be? The sum of the probabilities. And what can that be equal to? Roughly equal to the length of the interval. Right? So for example, if I take an interval of the form 1/3 to, let's say, 2/3, right? It's not exactly of the form of this particular form, but then I can still approximate it as a union of intervals of this particular form for large enough I. Right? And then you can sort of convince yourself that it should indeed be the probability that x lies in this interval should be 1/3. So this is the main reason why you look at random variables, because now remember the original experiment that I had was an infinite sequence of coin tosses. Now I mapped that infinite sequence of coin tosses to a random variable. So every realization of an infinite sequence of coin tosses can now be represented as a number between 0 and 1. Correct? And what distribution does this correspond to if it's a fair coin? Yeah. Over the reals, what distribution does this correspond to? So because right now I'm saying that the probability that x lies in the interval a to b is b minus a. So this essentially corresponds to the uniform distribution on 0, 1. So this was, I had one particular experiment, and now I've brought it down to an abstract random variable. And now I can sort of work with this space. I can just work with the reals instead of worrying about what my exact experiment was. So if I have tools to work with random variables in general, I can work with any general experiment. Correct? Right. So in order to work with random variables, we of course we've defined a probability measure, but we also have different ways of expressing probabilities. So if we have, so given any random variable, we know that every interval of the form a comma b should correspond to a valid event in our event space, right? Which corresponded to the original experiment. So keep this experiment in mind, that is infinite sequence of coin tosses. So I can view this as an infinite sequence of coin tosses, or I could also view this as a uniform distribution on 0 to 1, random variable which is uniformly distributed between 0 and 1. Right? Because sometimes it's easier to work with uniform distributions on 0 to 1 rather than coin toss, infinite sequence of coin toss. So each of these has to be a valid event, which means that the probabilities of each of these events should be defined. Correct. Now I can trivially look at events of this particular form, right, which corresponds to the event that x is less than or equal to b. And the probability for each of these events should be well defined, and that just corresponds to the probability that x is less than or equal to x, which is the CDF. So given any random variable, the CDF is always well defined. It could be a discrete random variable, it could be a continuous random variable, it could be a mixed random variable. But the cumulative distribution function, which is the probability that x is less than or equal to x, is always well defined. Now, depending on whether the random variable in question is a discrete random variable or a continuous random variable, you can instead work with either the probability mass function or the probability density function. Right? If it's a discrete random variable, then we always work with the power set. Your sigma algebra, you can just consider the power set to be your sigma algebra. So every outcome, you can assign probabilities to each outcome. But on the other hand, if your random variable is continuous, then what is the probability of one particular outcome? It's 0. So it doesn't make sense to talk about probabilities of outcomes. But then we would still like to work with something similar to the probability mass function. So we can try to define the probability density function. If the random variable, if the CDF is differentiable, then you can define the probability density function. Remember that not every continuous random variable has to have a probability density. Okay, but at least throughout this course, we'll either deal with discrete random variables or with random variables which have a well-defined probability density function. Okay, and here are some common distributions that we'll keep working with, and you should know the definitions of all of these. Right? I won't go through these in this class. These notes will be shared with you. So make sure that you know what is the probability mass function, what is the probability density function, or the CDF for each of these random variables. Right? And in your first assignment, you'll also calculate the mean, variance, and so on for these random variables. Okay, we'll frequently come back to each of these as we go. We need some other tools. So expectation. So you know the definition of expectation. If x is a discrete random variable, then the expectation is summation x times the probability mass function of x. And if it's a continuous random variable with a well-defined PDF, then it's just the integral x times f of x dx. Okay. So again, in this course, probability mass functions will be represented p subscript x. So the subscript will denote which random variable I'm working with, and it's p subscript x if it's a probability mass function, and f subscript x if it's a probability density function. You can also compute expectations of functions of the random variable, and they're just defined accordingly. There are two functions that we'll frequently be interested in. One is the mean, so expectation of x. The other is the variance, which is expectation of x minus expectation of x the whole square. I'll denote the mean by mu typically, and the variance I'll sometimes denote by sigma square, but sometimes I may use a different notation. Okay. Another key expectation that we will be interested in is the moment generating function. Now, just as we have the mean and the variance, you can define the kth moment as expectation x to the power k. This is sometimes called the kth non-central moment, and expectation of x minus mu whole raised to the k, which is the kth central moment. And the moment generating function is just expectation of e to the power lambda x for some lambda greater than 0. Right? And why is this called the moment generating function? So you can find the kth order moment just by taking the kth derivative and setting that to 0 and evaluating that at x equal to 0. Right? All right, so there is that. Okay, so now we've covered some of the basics. Our goal will always be to find bounds on these tail probabilities that I talked about in the previous class. Right? So given a random variable, I'm interested in quantities of the form probability that x is, let's say, greater than some particular delta. All right, and I want the tightest bounds possible for general random variables x. Now, for a given distribution, I can try to compute, I can maybe evaluate a closed form expression for this, or perhaps numerically evaluate it. But in general cases, even when I don't know the distribution exactly, or when the distribution is like very difficult to compute, I still want a reasonably good bound for probabilities of this particular form. All right. So these are called tail bounds, and much of this course will be on deriving tail bounds for various kinds of random variables. So hopefully you've seen this inequality in your probability course, Markov's inequality. So if you have x being a non-negative random variable, which means that probability that x is less than 0 is equal to 0, and it has a well-defined mean, so expectation of x is equal to mu, and I'll assume that the expectation is finite, then the probability that x is greater than or equal to t is less than or equal to the mean divided by t. Right? So has anyone not seen this before? Okay. So for starters, let's just derive this particular inequality. How would you derive this? Any idea? All right, so we have mu. What's an x? Let's for now assume that x is a continuous random variable. All right, what is the expression for mu? It's integral x times fx of x dx. What is the range of x? Since we know that probability that x less than 0 equal to 0, this is just integral 0 to infinity of this particular quantity. Now, let me split it into two terms. One, I split this integral from 0 to t, x times fx of x dx, plus integral from t to infinity, x times fx of x dx. Okay. What can I say about these two quantities? What can I say about this particular quantity? It's always going to be at least non-negative, correct? So this quantity is for sure going to be greater than or equal to 0. So I can say that mu is greater than or equal to integral from t to infinity x times fx x dx, right? Now in this particular integral, I know that x is always greater than or equal to t, correct? So let me take a bound. A lower bound for this is greater than or equal to integral t to infinity t times fx of x dx. We all agree? Integral t times fx of x dx, t to infinity. I can simply take t outside because of this. But what is this quantity equal to? Integral t to infinity fx of x dx. It's the probability that x is greater than or equal to t, right? So this is t times the probability that x is greater than or equal to t, which is exactly what I wanted, right? If I take t on the other side, if I divide this by t, I have mu by t greater than or equal to probability that x is greater than or equal to t. So probability that x is greater than or equal to t is less than or equal to mu by t. This is a basic bound, and it's not particularly good, right? In most applications, this turns out to be a very weak bound. And of course, it works only for non-negative random variables. But on the other hand, it turns out that this is very useful in deriving tighter bounds. Although the Markov inequality is in itself pretty weak, it surprisingly can be used to derive much better bounds for much general random variables. Right, so we'll see one such example right away, the Chebyshev inequality. Right, suppose I have a I have a general random variable with finite mean and finite variance. Okay? I want to know what is the probability that you deviate from the mean by a certain amount. So in the example of, let's say, n coin tosses, I have x to be the fraction of heads. And we know from experience that if you toss a coin multiple times, the fraction of heads is roughly close to a half. Correct? And that can be obtained using one way to obtain that is using the Chebyshev inequality. So it says that if x is a random variable with finite mean mu and finite variance sigma square, then the probability that x deviates from the mean by an amount greater than t is less than or equal to the variance divided by t square. Okay? And in fact, we'll use Markov's inequality to prove this. So I want probability that mod x minus mu is greater than t. I want to use Markov's inequality to derive this, right? What can I say about mod x minus mu? it's a non-negative random variable and it's always greater than or equal to 0. Can I directly apply Markov's inequality here?
That's square it.
I could, yeah. So in principle I could, but then I need expectation of mod x minus mu, which I don't know right away. I'm not given that information. I'm only given the mean mu and the variance sigma square. Correct? But this is equal to the probability that x minus mu the whole square is greater than t square. Because both sides are non-negative. So mod x minus mu is greater than t if and only if x minus mu the whole square is greater than t square. Okay. Do I know? So if I just apply Markov's inequality, I assume that this is a random variable y, this is t square. So what does Markov's inequality say? This is less than or equal to the expectation of y divided by t square. But what is the expectation of y? It is just sigma square. So this is less than or equal to sigma square by t square. Okay, so now using Markov's inequality, which was for non-negative random variables, I now have a general tail bound for random variables, for general random variables. But of course, it's a special kind of a bound because it only tells me how much you deviate from the mean. Correct? So let's just quickly go back to Markov's inequality and see when this is useful and when this is not. Now I have a non-negative random variable, correct? What can I say about the mean? The mean is also going to be non-negative, right? Great. So let's assume that the mean is say 0.2, just as an example. For what values of t will this bound be meaningful or useful? For example, what is the probability that x is greater than or equal to 0.1? What bound does this get? Less than 2. Is that useful? It's not, because the probability should be less than or equal to 1. Right? So when is this bound useful? Only if t is strictly greater than mu. Even if it's equal to mu, it's not helpful because I just get 1, which I know trivial. Correct? So that's a limit. That's another limitation of Markov's inequality. But in many cases where you know nothing about the random variable except its mean, this is sometimes very powerful. So in general, Markov's inequality by itself gives the weakest bound, and you can get much better bounds. And the reason why I keep saying that this gives the weakest bound, it's not very good, is mainly because of how this bound depends on t. Correct? So I want the probability that x deviates from something by an amount equal to t. How is it as a function of t? In this case, it grows as some constant, is the mean, divided by t. So it's inversely proportional to t. But if I look at the Chebyshev inequality, again, it's some kind of a tail bound, probability that mod x minus mu is greater than t. But now what is the dependence on t? It is 1 over t square, which decays even faster than 1 over t. Right? So I always want to derive bounds which has the best dependence on t. The faster it decays with t, the better. Right?
So,
Yes.
in Chebyshev inequality, we have to assume that t is greater than 0.
We have to assume that t is greater than 0. That's true. And because after all, we are interested in the deviation of x from mu, so we will always assume that it is strictly greater than 0. Yes, question.
So, expect that Markov inequality is negative. So,
In what situations does... So in general, Markov's inequality is used when, that's what, you know nothing about the random variable except the mean. Either it's very difficult to compute the variance, or at times you don't care what the mean is. You know the mean is something very, very small. You have a non-negative random variable, the mean is very, very small, and you have a large enough t. Okay. Correct, yes. But in general, other inequalities will give you much better, but it works only when you have additional information about the random variable in question. Because here the assumptions you have are in some sense pretty minimal. You know the mean, you know that it is non-negative, and that's it. In many cases, you can't even compute the variance. We'll see examples of some of those later. But if you can compute the variance, then typically Chebyshev inequality will be much better. Okay. Now, for individual random variables, these bounds are okay, interesting, but it becomes much more useful and much more interesting when you look at sequences of random variables. So, for example, if I have a single coin toss, sure, I can try to evaluate these bounds, but they're not very useful because I know the probability of a head and the probability of a tail. It becomes much more interesting when I have a sequence of coin tosses. I have a sequence of n coin tosses, and I want to know what is the probability that the number of heads is greater than, let's say, 100. Okay, so the kind of, at least for now, we'll focus on sequences of random variables which are independent and identically distributed. So I have x1, x2, x3 up to xn. Each xi has either a PMF px or a PDF fx. Right? So they're all identically distributed, and the joint distribution of x1 through xn simply is equal to the product of the margins. If this happens, then we say that these random variables are independent and identically distributed. All right. So at least for much of this course, we'll be looking at independent random variables. Later on, we'll look at independent but potentially non-identically distributed random variables.
So what is identically?
Every random variable, each xi follows the same distribution, some px. There is some distribution px such that pxi is equal to px for all I, and the joint distribution is just equal to the product of the px. It is the same for all. Right? Any questions? Okay. Now let's go back to our example of coin tosses. Right? We want to find the fraction of heads, and I can represent that as, let's say, y equal to 1 over n summation I equal to 1 to n xi. So I want the empirical average of all these random variables x1, x2, x3 up to xn. Correct? And we'll assume that all these xi's are independent and identically distributed. So what is the expectation of y equal to in this case? It's just the expectation of x, or the expectation of x1. What is the variance of y equal to? Correct. So the variance of the sum is equal to the sum of the variances. So this is equal to variance of 1 over n summation I equal to 1 to n xi. But what is variance 1 over n times this? 1 over n squared times the variance of the sum, which is equal to the sum of the variances, equal to 1 to n variance of xi, but they're independent and identically distributed. So each variance is just equal to, let's say, sigma square. So what I get here is n times sigma square by n square, which is sigma square by n. Okay. So if I take the empirical average of n IID random variables, then the mean is equal to the true mean. The variance is now reduced by a fraction of 1 by n. Right? So now if I just apply Chebyshev inequality, right? So again, come back to our example of n coin tosses. What is the probability that the fraction of heads deviates from half by an amount epsilon? Correct. So it is sigma square by, so sigma square by n, the variance of this random variable is sigma square by n, divided by epsilon square, which is sigma square by n epsilon square. So if I fix any small epsilon, could be let's say 10 to the power minus 3, as I let n to tend to infinity, what happens to this? It tends to 0, right? So this tends to 0 as n tends to infinity. Correct? So now this gives evidence to our empirical observation that if I toss a coin n times, if n is large, then with high probability I will see that the fraction of heads is very, very close to a half. Correct? And the decay is, at least according to this, it decays as 1 over n. But as it turns out, you can prove an even title. Let's see that in the next class. But this suggests that there is some sort of a convergence phenomena going on. As I let n to tend to infinity, as I let n grow larger and larger, if I look at this particular random variable, 1 over n times summation I equal to 1 to n xi, this is converging to mu in some sense. Right? So just as you have a sequence of numbers, we can talk about sequences of numbers converging to another number. We can also, at least conceptually, think about sequences of random variables. And our usual notion of sequences of numbers converging to something is not enough to understand sequences of random variables. And there are different notions of convergence, some of them stronger, some of them weaker. Over here, what did we see? We saw that if I look at this particular, if I call this yn, the empirical average of n random variables, I know that this converges to the mean in some sense. And it converges in this precise sense. So the probability that mod yn minus mu greater than epsilon tends to 0 as n tends to infinity. And this is called convergence in probability. So if I give you a sequence of random variables, we say that this converges to some other random variable x in probability if the probability that xn deviates from x by an amount epsilon, this tends to 0 as n tends to infinity.
The word here converges to extreme probability.
Correct. So that's a standard term. It's just a term used, so it converges in probability. Okay, and we'll sometimes denote this as xn tends to x. Maybe since we're almost out of time, let's stop here. Any questions so far?
It will converge to mu in some sense.
Correct.
That sense is different.
So in this case, I mean, this exactly corresponds to this definition, right?
This sense is always different for all the sequence of
So not every sequence of random variables may converge in probability to something.
So if it is converging, then definitely
We'll see that there are other notions of convergence. And you can have convergence in some notions, but not others.
so that notion also